In this video, I am going to go over what's called the Method of Frobenius. I think that's how his name is pronounced. I've only ever seen it written, but it's spelled Frobenius. So the Method of Frobenius, which is very common when you're reading books about the special functions. And so if we have this second order ordinary differential equation here, so what we can do, and since we know that we're only at second order here, that this will be analytic around x equals 0. So it'll be analytic there because we have it in the form of so if we had the 1 over x squared as the sort of highest order of x in the denominator here, that we can sort of multiply it by x squared and get everything out of the denominator. And so that's the form that I have it written here. But when we are working with it, what we are going to do is we're going to essentially just divide the whole thing by 2x squared, which will cancel out with this. It'll do something with this and this, which I will show right here. So we will end up with the second derivative with respect to x, and we've canceled this out here with that. Then plus, and what this will end up being, so I'm going to write it like this, so 1/2 plus x over x. And so we see that one of these x's canceled this one out. Well, so we end up with just an x in the denominator. And then this 2 divided by this 2 just gave us x, and then the 2 divided by 1 gave us this 1/2 here. And then this is multiplied by the first derivative with respect to x. And then we have minus, so this is still a minus. And then we have, I'm going to write it like this, so 1/2 over x squared. And I could have written it like 1 over 2x squared, but I'm going to keep it in this form right here. And so we see that if we look at these in our sort of general second order ordinary differential equation, we have that p of x is equal to the 1/2 plus x over x, and our q of x is equal to the minus 1/2 over x squared. And once again, we see that this is still, like I said, a regular singular point, because the x squared in the denominator here is the highest power in the denominator. I'm going to sort of just separate that out here because we're going to keep working on this one. And so what we will do is we will use what's called the Frobenius, I'm just going to keep calling it Frobenius series solution. And that is a series that has sort of the general form of, well, we could say that it is y equals x to some power multiplied by our power series here. So a naught plus a1x plus a2x squared, and so on off to infinity. And so this will end up being a naught x to the m plus a sub 1 x to the m plus 1 plus a sub 2 x to the m plus 2 and so on going to infinity. So this is the form here that this right here is the form of our y. So we are saying that this should have put the y up here, so that's still multiplied by our function. So this y is going to have a form that looks like this, with this x to the m in front of it. And so then our dy dx, so sort of going term by term and taking the first derivative of each of those is going to have a form that looks like a naught m x to the m minus 1 plus a 1 m plus 1 x to the m plus a 2 m plus 2 times x to the m plus 1 and so on, going to infinity. And then if we took the derivative of that, so that would be our second derivative with respect to x, what we would have is a naught m times m minus 1, because we would now be taking this m minus 1 down to the front here and lowering that to x to the m minus 2 plus a1 m plus 1 times m x to the m minus 1, and that will sort of keep going on in that fashion. So well, I'll put one more term here, so it'll be a2 m plus 2 m plus 1 and then x to the m and so on. And so if we put that back into our equation up here, our differential equation up here, what we end up with is, so we first put in the second differential, and so that will be our a naught m times m minus 1 times x to the m, write that m a little bit better, m minus 2 plus a1 m plus 1 times m plus 1 times m times x to the m minus 1 plus a 2 m plus 2 m plus 1 times x to the m, so on, going to infinity. But then we will add on to that, so plus, and we have our so it's our 1/2 plus x, and so yeah, so plus x, and the net is multiplied by our, so that 1/2 plus x, remember, is our from our p to the x, and we will see what happens with this x down here. So, well, essentially what's happening is, see, we have this x to the m minus 1 here, so that x is going to cancel out with that, so we end up with a naught times m times x to the m minus 2, because that x in the denominator canceled out with that, and then plus our a1 m plus 1 times x to the m minus 1 plus a 2 m plus 2 times x to the m, and so on, going to infinity. And then we have our plus, and this will be, well, actually that's going to be a negative, because remember it was minus 1 half times a naught times x to the m minus 2, because remember up here we had x to the m, but we are dividing by this x squared here, so we end up with the x to the m minus 2 right there, and then we have plus a sub 1 x to the m minus 1, because once again remember up here we had a sub 1 to the x, and then we're dividing by x squared, so that gives us an x to the m minus 1 right there, and then plus a sub 2 x to the m, and so on, going to infinity. And so we can see that that x to the m minus 2 is just equal to x to the m over x squared. And so if we divide by x, to the m minus 2, so x to the m minus 2, that is equal to x squared over x to the m. And so we can cancel out these common terms of x to the m minus 2 by essentially dividing by this x to the m minus 2 here, because what we end up getting is if we have our x to the m, that's an x, over x to the 2 times x to the 2 over x to the m. So this multiplication is the same as dividing by x to the m minus 2. So everything is just going to cancel out, and this ends up being 1. And so we can see too that if we have x to the m minus 1, which is x to the m over x, and we multiply that by x squared over x to the m, that this will end up equaling x. And so by dividing everything by x to the m minus 2, or multiplying it by x squared over x to the m, we can get rid of these common factors of x to the m minus 2, and what we end up getting then, after going through term by term and doing that, is we end up getting a naught times m minus 1 plus a1 times m plus 1 times m, x plus a2 m plus 2 m plus 1 x squared plus, and then we have our next term here, which is the first derivative, and remember that had that 1 half plus x, and then we had the a naught m plus a1 m plus 1 x plus a2 m plus 2 x squared, and so on to infinity. And then we had the minus 1 half, and then we can do it like this. So a naught plus a1x plus a2x squared, and so on, going to infinity. And remember this, I should put to that this is all equal to 0, so we're still equating this to 0. And so just by dividing every term by this x to the m minus 2. We took this and sort of simplified it down, got rid of a little bit of that, those exponents and everything, and ended up with something like this. And then what we can do is we can combine the corresponding powers of x. So we see here we have this 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 a naught m times m minus 1, which is from our first term, so m minus 1. And then we combine that with this a naught m, and we have to multiply this through, so we end up with plus 1/2 a naught m, and then we have this minus half times a naught, so we have minus 1/2 a naught, and that should equal 0, because we are saying that a naught is not equal to 0. Then if we factor all this out, or we factor the a naught out, we have m times m minus 1 plus 1/2 m minus 1/2 equals 0. And since we said that a naught is not equal to 0, then this part here has to be equal to 0. And so we can just focus in on that, and we end up with m minus 1 plus 1/2 m minus 1/2 equals 0. And we can do the same thing for the other powers of x. So we can go through and just combine all the other powers of x. And what we will end up getting for the a1 is we will get something that looks like m plus 1 times m plus 1/2 times m plus 1, and then minus 1/2, and that should also equal 0. For the m, or for the a sub 2 terms, we will get m plus 1 times m plus 2 plus 1/2 times m plus 2, and then minus 1/2, and that equals 0, and so on. So we could do that to infinity, really, because there are an infinite number of these this here should be an a, so an a sub 1. But anyway, like I said, these go off to infinity, but what we end up having here, these are called our indicial equations. So these are what are called the indicial equations. And they are just obtained by taking each of these coefficients and just taking the terms that these with the corresponding coefficients in each of these series here, and just equating them to 0. So from the indicial equation, what we do is we actually get the roots for this. So we want to find so we can see that this is second order, because if this m is distributed in the air, we end up with an m squared. So we can see that we're going to end up with two different roots, and so the first one is going to be so the first one is 1, and the second one, m2, is going to be minus 1/2. So if we put 1 or minus 1/2 in for any of these m's, then we end up with a 0, if you remember your quadratic equations. And so from these different m's, we can calculate the coefficients that we want. So if we have our a sub naught, and so that's from this up here. And so if we just rearrange that around so that we can solve for a sub naught, what we end up with is 1 half minus 1 half m over m times m minus 1. And so this is how we would get the a naught, and we would solve it twice. We'd solve it once for m equals 1 and once for m equals minus a half. And we can get the other coefficients in terms of a sub naught, so we can get this. So we end up with something that looks like m plus 1 times m plus 1 half m plus 1 minus 1 half. And in the numerator, we will have minus a naught times m. And so we can keep solving these coefficients in terms of the lower coefficients that we already know here. And so from there, if we solve for each of these coefficients, what we end up with for our original equation is we end up with two different solutions. So and the two different solutions come from these two different m values here. So if we solve this for m equals 1 and then this for m equals 1, we end up with this solution where this is x to the 1. So we have the m equals 1. So remember, we started with our Frobenius series solution with x to the m. So the first solution is going to have x to the 1, since m equals 1 is our first solution. So you can put a 1 up there. I think I'll just leave it without the 1. Then that will be multiplied by 1 minus 2 fifths x plus 4 35ths x squared, and so on. And we end up with y2. So solving all of this for this m equals minus 1 half, we end up with x to the minus 1 half, and that is multiplied by 1 minus x plus 1 half x squared, plus going off to infinity. And so then we can say that our general solution is y equals, and we could multiply it by some constant, times x, 1 minus 2 fifths x plus 4 35ths x squared, plus going off to infinity, and then plus c2 x to the minus 1 half times our 1 minus x plus 1 half x squared, going off to infinity. So this is our general solution for y right here. So we found a solution. Remember, in differential equations, a solution is finding a function that makes our sort of original equation up here true. So we're finding a function that makes this up here true. So all this equal to 0. We're trying to find these y's here. So the y that satisfies all this, and going through this Frobenius method, we found that this is the y that satisfies that equation up there. So there's a little bit of difficulty when it comes to the Frobenius method too, and that is that if m1 equals m2, or if m1 equals m2 plus n, where n is equal to some integer. Uh, I think it actually has to be a positive integer, but I don't remember offhand. So we'll just say an integer, but I think it might be a positive integer. But anyway, if m1 and m2 that we got from our initial equations up here were sort of equal to each other or some integer uh, sort of multiple of each other, um, then this then there it's possible that there is no second solution. So I showed up here that we have these two different solutions here. So solution one and solution two. Uh, if we have this though, then there might not be a second solution, or it's possible that the second solution has some added term to it uh, that is sort of y1 multiplied by the logarithm of x uh, plus our second solution, which once again would have the form of x m2 times our a naught plus a1 x 1 plus a2 x squared and so on. So this would be the form of the second solution. So we would end up with something where we have to multiply our first solution by the log of x plus our x to the m2 times the a naught plus a1 x1 plus a2x squared and so on. I'm not going to go too into depth on how we end up getting this this here because this actually has some other constant multiplied by it as well, and you have to find out this constant here. But what I really wanted to show in this is just this method of Frobenius, because in the future videos I'm going to kind of skip all these steps here when actually looking at how to find the solutions to the various differential equations that we are interested in. So the sort of general differential equations for where the Hermite polynomials, the Hermite polynomial. So we're going to look at Legendre. We're going to look at Bessel, and we're going to look at I don't remember how to spell it, but it's like Laguerre or Leguer or something. But anyway, all the once again, the point of doing all this is to look at these special functions that we will have coming up as solutions in the Schrodinger equation. Solutions to the put the little umlaut there, Schrodinger equation. And so, like I said, the motivation for doing all this differential equation type stuff is to sort of look a little deeper at these special functions here that will be coming up in solutions to the Schrodinger equation. And like I said in a previous video, the reason I'm doing that is because, at least for me as a self-learner, when I was sort of reading through, in particular, the Griffith's book on quantum mechanics, these various types of special functions started popping up because they are solutions to the Schrodinger equation, which we will see are solutions to spherical spherical harmonics, and they're just kind of introduced, and it's not really explained what they are and why they're there. So I thought, well, I mean, in my own journey of self-learning, I went and bought some books about these special functions and sort of led me down this rabbit hole of looking into differential equations and special functions and even into abstract algebra and stuff like that. And so there's sort of a lot of baggage or background that comes with looking at these special functions, which, as I said, are needed for spherical harmonics, which are solutions to the Schrodinger equation. And so I wanted to go over just a little bit the I guess properties of these functions that as they relate to the Schrodinger equation. And as I said, uh, this Frobenius method is something that pops up a lot when you're looking into these special functions. And so when I'm looking at these special functions and their and the polynomials and stuff that come up as solutions to different general types of differential equations, I'm going to sort of uh, gloss over a lot of these steps here in the Frobenius solution. So I thought it would be a good idea to have a video that's just sort of specifically focused on the Frobenius solution. And so it doesn't seem like just a lot of voodoo, I guess, when I'm going through that in later videos. But anyway, I'm kind of rambling now. I hope this video was at least somewhat helpful to you and will be helpful to you down the line in future videos. So I will see you then.